So you said number 45. I think we can do that. Oh boy, with the dark skies outside, turn out those two lights. Sleepy time now. All right, so 45 says 5 kilogram block hangs from a spring with a spring constant of 2,000 newtons per meter. The block is pulled down 5 centimeters from the equilibrium position and given an initial velocity of 1 meter per second back towards equilibrium. What is the frequency, amplitude, and total mechanical energy of the motion? Solid question. I would say that if you can do those three things, then you'll be able to do 75% of what I'm going to ask for you to do on the practice FRQ today. So we're going to do a practice FRQ after this. I already posted it, so you'll be able to see it there, but we'll talk about it. 2,000 newtons per meter, mass of 5, and they pull it down 5 centimeters. So I assume we're at equilibrium right now, and it is pulled downwards 5 centimeters. But when here, it's released with an upward velocity of 1 meter per second. Is that all the parameters as you guys heard it? That's what it sounded like to me. So they asked then for 3 things: the frequency, amplitude, and total mechanical energy. Well, this information about how much it's been pulled down and all that, none of that affects the frequency. So let's handle that one first. That's the easiest of the questions to answer. We have the mass, we have the spring constant, so we can find the frequency directly. I don't really have to put the numbers in. I think we're probably good here. Is that enough for you to know what to do next? All right, so I'm going to skip that part and go on to the next part, which I think is more interesting. He wants the amplitude and total mechanical energy of the motion. So be careful here. When it says total mechanical energy of the motion, that's deceptive. So I guess we'll deal with the amplitude first. We're going to be solving these two things at the same time. So when it asks for the amplitude, we need a way of measuring the distance from the equilibrium position to where the mass comes to rest. It comes to rest in 2 different places, someplace up here and someplace down here. You guys agree with what I'm saying? So we need to find where one of those 2 places happens to be. This is equilibrium. This is where mg equals kx. So which one do you guys want to look for? The bottom one or the top one? It's not going to make much of a difference, but I see one person mouthing the word bottom one, so we'll go with that one. The lowest position will be the position where the object has all the energy in elastic potential. That's the lowest point in the motion, so there's no gravitational potential. The object will be stopped, so there's no kinetic. Does that make sense? All right. We know that at this 5 centimeter position, the object has energy equal to 1/2 mv squared plus 1/2 kx squared. But what you also have to realize is that whatever height this is, the object has gravitational potential energy as well. And that has to equal whatever the 1/2 k, it's not even amplitude here. It's the fully stretched amount of the spring. Does everybody understand what I'm saying? So I need different numbers here. This one I think I need to draw something else. I'm sorry. But you asked for doing the bottom one. We need to figure out what this is. We need to figure out where the equilibrium position of the spring is. Can somebody do that real quick? Just use 10 for G. Yes, sir. 0.05? 0.025. All right, so x equals 0.025 meters. Here's why we need that. If the mass wasn't there at all, the spring would have been up here someplace, correct? We put the mass on the spring that causes the spring to extend, storing elastic potential energy in the spring. We pull it down an additional 5 centimeters, so the amount of total energy in the spring at that moment has got to be 0.05 plus 0.025. That's how much total kinetic energy is in the spring. I'm sorry, total potential energy in the spring. We also know that it has a certain amount of kinetic energy because it's moving at 1 meter per second. Doesn't matter that it's moving up or down. But we still don't know how far from the bottom it is. We do know that this number here is the fully extended spring. So that's got to be 1/2 K 0.025 plus 0.05. I'm out of space. Plus H. And of course I have all of this. 1/2 M times 1 squared plus 1/2 K times whatever all that crap is plus MGH. So this is just 0.075 there. Now, I know this looks messy, and it is. And it looks like there's going to be 2 answers for H. And there is. One of them will make sense. One of them won't. But we need whatever that answer is for H. So I'm going to pause for a minute, let you guys bang away at those numbers, because we have the mass and we have the spring constant. So I think you guys could probably work out a solution here. This is 1/2 times 5 times 1 squared plus 1/2 times 2,000 times 0.075 squared plus 50H equals 1/2 times 2,000 times 0.075 plus H squared. Boy, that's messy, isn't it? Sounds like there's craziness outside. It's tough. This is a tough one. Yes, ma'am. I couldn't hear you. You could try again. bit about this one. This is the one where there's a box on top of a box. And there's a spring here. And we're told the system is oscillating back and forth. They give us information about it. They tell us the period is 1.5 seconds. And the amplitude, okay, it says the upper block begins to slip when the amplitude is 0.4 meters. Okay, so in your notes, pay attention. I would put something in your notes about this problem specifically. There's several versions of this problem. There's this one where friction is deciding how this box moves. There's another version of the problem where the spring is vertical, the box is placed here, and another box is placed on top. And the system is oscillating up and down, and you want to find out how much it has to oscillate until the box on top separates from the box on the bottom. These are very much similar questions. They deal with thresholds. There is a limit to how much this can oscillate without the top box sliding off the bottom box. So what force causes the top box, get that out of the way, what force causes this top box to move back and forth? The spring does not. The spring's not in contact with the top box. I've heard a few people say it, but what force is actually moving the top box? Friction. Friction moves the top box, and friction has a limit because this is static friction. This is the maximum amount of frictional force available. You can have less, but you can have more than this. So there's a maximum amount of force that can be applied at the surface before static friction will break. If I exceed that amount of force, then the box will slide off. Now, if you don't understand what to do next, the only force acting on the top block is friction. So the net force on the top block equals MA for the top block. And again, the only force that's acting is friction. So at A max, my friction can't exceed this. At A max. If A max exceeds that, then there's not enough friction to cause the box to slide, or to stay in contact with the bottom box. So I need to ensure that mu s mg is greater than or equal to MA max. Now, A max is x naught omega squared. They told me it just begins to break when that is 0.4 meters. What's left? Well, I don't know the spring constant, and I don't know the mass. But I do know the period, which has to be equal to 2 pi over omega. Which means omega equals 2 pi divided by 1.5. So I have omega. I have what I'm supposed to use for x naught. Pretty sure I know g. We're trying to figure out what is the required coefficient of static friction. That's it. Plug them all in, find your number. It's a good question. Solid. It's hard. Got all sorts of physicsy stuff in it. I like it. All right? All right, we're going to change. This one for us to look at as a class discussion today. It's been sent to you already as an assignment I'd like you to turn in. You will get credit for working the problem in class today. You're going to want these in-class credit opportunities. I've also assigned, right now, this one. You should have it sent to you because I don't think I can make this big enough for you to read it. And like I said, I've got... All right, so in order for us to have time to kind of talk this through, and so I feel like you have enough information to be able to make it to the next one, let's talk about some of these. I don't think I have to do part A. I think you guys got that. I would have done square root of 2gh. I mean, you could do conservation of energy the whole route, but you understand it just fell 0.45 meters. So find a method, but that one should have been pretty quick. Question B, do you realize that feels like one of the only parts of this, that simple harmonic motion, that's just a plug and chug? So did you use the equation for period? Just put it in there. You don't have to have any prior information for that one. We're not going to get a whole lot of points here, but if you could get those two, then you've cleared, you're up to a 2 on the exam. You just need to get a couple more points to get to a 3. Those are the ones that make sure you know the basics. And a lot of students probably missed part C. But you can still do more of this problem. But part C was the crux. And don't make that mistake now. This is common to have something dropped like this and to not fully appreciate where the reference levels are in this problem. The amplitude is going to be some distance where it oscillates back and forth across the equilibrium position. So when you did this, you found the location of the equilibrium position. So you're going to use that for the rest. Now, question D, determine the maximum compression of the spring. You have a choice on how you do this question. And so in the other class, I did it one way. In this class, we can do it another. It's up to you guys. Here's your choices. We could try and figure out what the amplitude of this problem is first, and then use that to figure out what the maximum compression is, because we know where the equilibrium position is. And we could probably use something like V max equals x naught times the square root of k over m, right? Our definition for V max. We could use that. And that's not on the equation sheet. And some people have been asking me questions about the equation sheet. You would have to memorize that to use it on the equation sheet. Or we could find out where this position is, the lowest position, and then use that to figure out what the amplitude is by subtracting it from the equilibrium place. It's your call. I'll let you guys decide which one we're going to do. The second one? All right. If we're going to do the second one, you have to be careful here. This is the lowest place. So all the energy here is elastic potential. Everybody agree? And all the energy up here is gravitational potential. So all we're having to do is say mgh equals 1/2 kx squared. Here's the problem. X is this distance. H is this distance. right? H has to be measured from the lowest point in the problem, and X is just how much the spring was compressed. So mgh is going to be X plus 0.45 equals 1/2 k x squared. This is a quadratic, and there are two answers here as well. If you want the answer, you'll need to solve this for x. It is interesting if you can get both answers here, because I think the other answer does have meaning, and I think it's important to talk about the other answer. So just do this. This is just a simple quadratic. I say simple, but that's on you. The whole negative b plus or minus square root of b squared minus, 4ac divided by 2a. We just can't go on until we have that, and it's 2 minutes until we, what?
I think, do you want me to do it?
No, I thought you were asking a question.
No,
You have the two x's?
I have one of them, and the other one's far deep in my calculator I did put in.
It's okay.
I got 0.4 or 0.42 and negative 0.2.
Okay. 0.42 and negative 0.21? Okay. Yep, this is what you get. Now, this is the one you want. This one's not, but this one has meaning. We just asked when the potential energy was equal to the elastic potential energy. Well, if you could pull the spring outwards 20 centimeters, apparently at that location, you'd have the same amount of potential energy. So somewhere right in here, if you could get the spring to come out to meet it, you'd be storing as much potential energy in the spring as you'd be at the change in height for the gravitational potential. So it makes sense, but is the spring going to reach out to meet the mass as it falls? Probably not, so I'm going to throw this one away. This is the maximum displacement of the spring. This is not the amplitude. The amplitude is 30 or 31 centimeters because you needed x from here. And you get 0.1 meters, I believe, here. So the amplitude is from here to here. That's how far the amplitude is. Or it's this total displacement divided by 2. Bye, folks. Look, whatever work you did in class today, upload that. I'm going to give you participation credit for playing along. And then you have a 15-minute practice tonight. Please do. Assign this one for you to do tonight. I will eventually send out a solution set, probably tomorrow morning. We're going to go over it first thing tomorrow before our quiz. Do you see why I think it was good for us to talk about the question we just talked about? This problem is similar. The box here, the 5 kilogram box, is attached to the spring. The 3 kilogram box is not attached to the 5 kilogram box. They're going to ask questions about how the system oscillates, and they're going to ask about what is the maximum amplitude before the 3 kilogram box separates from the 5 kilogram box. I'm going to give you a hint right now to use in your homework. The downwards acceleration of the system has to be less than g. If the system accelerates downwards faster than g, well, then the 3 kilogram block will be left in the air, because the max acceleration that the 3 kilogram block can experience downwards is g, right? It's not attached. So if this one accelerates faster than g, this one can only accelerate at g, they'll separate. So your downwards acceleration, the A max downwards, has to be less than g. That should help you with that question. Today we talked about this question. What I'd like to do is I'd like to give you a quiz tomorrow. an FRQ quiz on simple harmonic motion. We talked about this one yesterday.